Okay. Okay, so we're ready to go? No objection? Action. So, hello people. I'm here to talk to you about a concept for password hashing, which I called delegation. And it's about making clients or other people work for you. So, I am Thomas Pornin and I work at CGI. This research is mine entirely, but CGI paid for this trip, so they have the right to have their logo. Okay, so the outline of my talks. First, I described a definition of what I call delegation. Then I describe a hashing function which is called MAQUA, which is a candidate to the PhD, and which allows you to do delegation. Then there will be a section about parallel hashing, and that one is not in the MAQUA specification, it's a new one, and that's where I'm going to kill all of you because there's a lot of math. And then we'll go to performance, and it's more understandable. Oh, you'll have to bear with me. And there will be a conclusion. And I've set up a perfunctory website whose URL is at the bottom, and there you will find a logo and a copy of these slides. So you can get the PDF right now, if you like. So, password hashing and delegation. Normally, you should already be aware of what we are talking about. We're talking about passwords, and the problem with passwords is that they are chosen and remembered by humans, and humans are not good at choosing good passwords or remembering them. So there are two main scenarios where an attacker could get something to run an offline dictionary attack. That is, the attacker could obtain a value with which he can verify on his own computers whether a potential password is the right one or not. So the two main scenarios that you will encounter is password-based encryption. There's some data which is encrypted with a key that it can be a file or your whole laptop disk. And another is the classical client authentication for a server, and the server has a hash password on the database, and it's unavoidable that the server stores something which allows the server to know whether he's talking to the right client or not. So if the attacker can steal the password, the server database, he can have these hash values. So this is I'm using a military metaphor because this is really a battle. It's a war. The attacker has a lot of advantages. First, he's patient. Average human user will want to be authenticated within 1 second, maybe 2. Definitely less than 5. However, the attacker may, if he really wants to get access to an account, he can spend 1 week on the problem. And 1 week is a lot more time than 1 second. The attacker also has a lot of passwords to try, not just one, so it's what they call an embarrassingly parallel problem. He can get parallelism as he wishes. Also, the attacker can buy some specialized hardware, so GPU, FPGA, whatever, because he's trying to do something difficult, but he can invest in some specialized hardware that the honest user will not have. The genuine user has a smartphone. And finally, there's Moore's law, which is a way to state that computers get faster every year. But the human brains do not get faster every year. So the amount of computational power that the attacker can invest in attacking will be greater and greater when compared with the defender's main resource, which is the user's brain. So on the defender's side, we've got source and slow hashing. Source is to prevent cost sharing, because there are many situations where the attackers wants to break an account among a lot of them, because through some SQL injection attack and so on, he got 1,000,000 hash passwords. And we want to make sure that the attacker will pay the cost for every password he's trying to crack. So it's got 1,000 passwords to crack, it will cost him 1,000 times the attack. So also for that. And slow hashing is about making the situation, it's about gaining some fairness to make sure it's making the function more expensive to release the countermeasure for Moore's law. We're making the function more expensive to cancel out the fact that the computers are getting faster. However, I don't want to be fair with the attacker. I want to beat him to the ground. So, here is how things goes. User sends his username and password, and on the server side are stored indexed by identifier, user identifier, the salt, and the hash password. Okay, that's very classical. You all know that. There's a concept which is called server relief, which is about pushing the hard work of slow hashing on the client side. So when you have a protocol with such things enabled, the protocol looks like this. The user first sends his ID, server returns back the salt, all the slow hashing, salty hashing goes on the client side, so it saves resources on the server, and finally, the client sends the password hashes, and what is stored on the server must be a hash of the hash. The outer hash is something which is fast. It's not a problem if it's a simple SHA-1 or SHA-256. But it must not be what the client returns, because we don't want to store something which is password equivalent. Server relief is fine, but it works only if the protocol supports the back and forth protocol. Okay, it's hard to push that in a web context where there is a simple HTML form. And also it will work depending on the power available on that specific client. So if he's connecting with, say, my smartphone, which is really old, it will take a lot of time to do the slow hashing, or it won't be a very slow hashing. So delegation is about pushing the hard work of hashing somewhere else. So from the client point of view, we are back to the standard protocol like an HTML form, but we arrange things so that the hard work of hashing can be delegated to third-party systems. And the really important word is the untrusted. We want to be able to make these other systems work for us, but we don't trust them. We don't want to show them the password to hash. We don't want them to obtain the hashed password, but only a value which is masked, which they cannot exploit to run an offline dictionary attack. If we can do that, but it takes mathematics, but if we can do that, then we can push the hard work on other systems such as the cloud-based system running in Muscle, or even the clients or other already connected clients. So that's basically what I just said. So delegation is about going to the battle against the attacker with more troops and enlisting other people to our battle. So we also want to be able to do parallel delegation, in which you are using a delegation to several distinct systems running in parallel for a single password hash. That's a third part of my talk, and I'll describe how this can be done. Unfortunately, you cannot do that with just any password hashing functions. You need an algebraic structure which allows you to do this delegation. And fortunately, there is a function which can do that, which is called Macwa, and I'm going to present it. So, it's a candidate to the password hashing competition. and it's based on modular arithmetics. It has a work factor which is CPU only. It's not memory hard. There's only one work factor, and the cost is proportional to that work factor. So from my point of view, it's rather an advantage because it's relatively simple to tune. Honestly, when I see password hashing functions with a memory cost and a time cost and the two tunable factors, I don't expect average system administrators to do the tuning correctly. There are just too many combinations. So when I'm on the sysadmin side of things, I prefer where things are simple with only one tunable, but that's debatable. The modular arithmetics is an algebraic structure which enables a lot of features such as delegation, but also doing an offline work factor increase. And there's also a possibility for a fast pass where a system who knows the specific secrets can compute the hash much faster or even recover the password from the hash, because it's not really a hash, it's an encryption, which you can use as a hash function. And the name is named after the name for the American black bear in an Algonquin language, the Ojibwe people. So this explains the pictures. It's a bear-themed function. So now here are the mathematics. So you take what's Bloom called a Bloom integer. It's basically an RSA public key, the modulus, with the extra property that the two factors must be equal to 3 modulo 4. If you take random RSA keys, 1 in 4 will be a Bloom integer. So it's not a difficult property to have, and it doesn't weaken the resistance of the factor against the integer factorization. And you want it to be large enough so that factoring the modulus into its prime integers is hard, actually infeasible. So the minimum size in the specification is 1280 bits, but I recommend, as usual, 2048. But if you want 2000 exactly, it's possible, whatever, the size you want. And if you take integers modulo n, then you can call the quadratic residues, these are the squares. And exactly 1 in 4 integers modulo n will be a quadratic residue. And squaring happens to be a permutation on that subset of integers modulo n. And it's even a mostly one-way permutation. That is, everybody can compute a square, but a square root is, as far as we know, infeasible without knowing the two P and Q factor. So that's my tool. And the main idea is that we hash a password by converting it into an integer modulo n, and then we square it a lot of time. The hard work is doing a lot of squarings. So it's not a new idea. It's a new idea for password hashing, but spending time without known shortcuts has been proposed since 1996. It was called the time lock puzzle. And it hasn't been tried in some protocols. And actually, I'm building on 18 years of research, and people will say, okay, that's there's no shortcut, and they've really looked hard and for quite some time. Of course, if you know the two factors, then you can use that as a shortcut, or now the permutation is no longer one way. And we're still doing things with mathematics, so we'll see in a few slides how this can be done for delegation. So the red square, that's where the time is spent. Everything else is just administrative. From the password, you've got first an optional pre-hashing. You do the hashing if you want to support passwords of arbitrary length. And when I mean arbitrary, that's arbitrary. If you want to type 2 gigabytes of password, do it. If you don't do the pre-hashing, you've got a size limit, which is at least 128 bytes. So that's rather large for passwords. Then the password, hashed or not, will be padded to turn it into an integer modulo n, and that's where the salt enters, and the padding is deterministic. Then you do the squarings, and you get on the output an integer modulo n, and possibly you hash it again if you want an unbiased output. That's a k-derivation function usage. So that with post-hashing, you can get the output of the length you want, so it can be short or long, and it's unbiased, so you can use for symmetric encryption or MAC or whatever. All the hashing steps use HMAC DRBG, which I should describe here. It's a pseudo-random number generator, which has been around for about 10 years. It's been approved by NIST and published, and moreover, its security has been in a way proven in 2008. It's a reduction proof, so someone who's called Yuose has actually proven that HMAC DRBG is similar to a random oracle as long as HMAC is secure and also fulfills some properties which are a bit technical to describe. And other people have demonstrated that HMAC appears to be quite good at that. And in practice, there's no known attack on HMAC DRBG. So it's not a new primitive. It already exists. There are even test vectors for implementations. And it appears to be strong and robust for everywhere you need a particular hash function with a tunable output length. Since it's used only in the pre and post hashing and the padding, but not in the core function where all the CPU is spent, the performance of that function is not relevant. So we don't have to concentrate on making it slow or fast. It does not matter for the security against password dictionary attacks. Okay, so when I must pad the password, I'm doing it that way, and if you ever implemented RSA, it should remind you of things. Basically, I take the password, I've got the password length on a single byte, so that the padding is reversible. That is, there's no it's not ambiguous. If I can find the padded value, I can recover the password if it contains zeros or some bytes like that. The padding is obtained by using the password and the source as input to HMAC DRBG, and we get at least 30 pseudo-random bytes, and the left byte is always set to 0, so that the resulting value is always smaller than n, so there's no modular reduction or bias at that point. And when we've got that sequence of bytes of the same length of the modulus, we interpret it as an integer with big endian convention, which is the classical convention for these things, except when we are Microsoft. And then you proceed to do the squarings. You do as many squarings as you need, but that's a work factor. So it's equivalent to raising the value to a power which is itself a power of 2. And for work factor W, it's raising to the power 2 raised to the power W plus 1. So you are doing W plus 1 squarings. The plus 1 is meant to ensure that people don't forget to do at least one squaring. It's important. So if you use the minimal work factor, you've got one squaring, and it's called Rabin encryption. And it's an asymmetric encryption system which has been described since I was about that high. So it's rather old, and it's still unbroken. And the cost is proportional to the work factor, which was what we wanted. So we can have a fast pass. The fast pass is when we know the two factors P and Q. For everything which preceded, you worked with the modulus alone, just n. But if you remembered the two factors, then you can do things much faster, because you can work modulo P and Q separately. And since they are prime numbers, you're no longer on a ring of integers, but on a field, and on a field, you've got more mathematics, and you can first reduce the exponent modulo P minus 1, and then you'll get a much shorter exponent, and you can do the exponentiation with this shorter exponent, so it will be much faster. And then you recombine everything with the Chinese remainder theorem. And basically, you can do the hash in a cost which is similar to RSA private key operation. So I've got a simple PC as a server, and it can do that with 1,000 times per second. So it's not free, but it's fast. And there are timing attacks which are possible, but that are exactly the same that you could find for RSA. So you can do the same countermeasures as RSA with masking and so on. And we are not in untrodden paths. It's a known territory. So the fast pass, I'll talk to it a bit later, but it was part of the call for candidates for the PhD, so that's why it's here. But it can be useful in some specific situations. And there's another feature here. That's what I just said. Okay. Here is the scenario where fastpass is usable, is interesting. Is when you have your hash password in a database and you have several front ends for several protocols which feed on the same database of hash password, and some of these front-end servers can be deemed more secure because they have a HSM for the key, or they don't run PHP or so on. They run some software which you would consider to be stronger. And in that case, it makes sense to put knowledge of the PNQ factor, which are really a private key, in this secured server, and this will be able to run things faster. That is, the hashing will be expensive, except for the defender, but it will be expensive for the attacker, and that's the nice situation that we really want. If you don't need the fast pass, which is a very common case, you can discard the P and Q factors. That is, you must keep them safe, but if you don't keep them at all, you've got perfect safety. So it so happens that this fast pass actually turns into an escrow. That is, you can reverse the squaring, and you can, if you know P and Q, you can compute square roots. So it's not exactly the same exponent, but you can reverse all the squaring. So not only you can hash fast a potential password, but you can go from the hash password to recover the password itself. So this highlights the fact that the P and Q factors are really sensitive information. So it's a private key. Keep it safe. Or don't keep it. Again, the cost is similar to an RSA private key operation. The escrow can be useful in some reasonably far-fetched situation. You can use it to recover forgotten passwords, if that's your thing. You can use it to support some protocols where the clear text password is needed. There's things like that in the POP email protocol. The APOP authentication mechanism is an old authentication mechanism, which is a challenge response. So the server must know in advance the clear text password. And we also know that there are system administrators who really love to look at the password of their users. They should not, but they really love to. So if they're going to have a look at the user's password, at least let's make it sure that they store them properly. So they can use the escrow to recover, and they can do it from the database and with the P and Q factor stored in their own laptops of an offline system, which is distinct from the online systems. You can get a fast pass and escrow with any password hashing function with just a trick. When you hash the password, you also, in a secondary value, you also encrypt the password with an asymmetric encryption system. With Macwad, you just have both values in one. So these are not extremely crucial properties, but they are convenient. At least you must be aware that they're here. A more interesting property is that you can do an offline work factor increase. This was also a requirement of the PhD, or I see at least a desirable feature, which is that we acknowledge that computers get faster over time, so the work factors must be increased regularly. The generic method for any password hashing function is to wait for the user to come again, because when he next authenticates, you have the password, so you can, at that moment, rehash it with a stronger, higher work factor. But with Macwa, and there are a few other PhD candidates which support that too, you can increase the work factor from the stored hash directly. And this has some nice properties from a practical point of view. First, this verify the password and rehash it with a higher work factor. It's additional logic. And additional logic, usually you live better when it's not on your front-end server, on your deployed system, which can be attacked and which is on the front line. You could do that as an offline operation that you run on the database itself, possibly at night, and from other computers which are not online at that moment. Moreover, this computer which has the offline work factor increase could know the P and Q factors, and if it knows the private key, then it can apply the fast pass. And if you have 1 million passwords to upgrade, 1 million hash passwords to upgrade from a work factor of 100,000 to 200,000, it's going to take some time because it's expensive. That's the point. If you use the fast pass, it's going to use a lot less time. That's the difference between being done within 1 hour or 1 week. And if you're doing that at night, because you're a responsible administrator, you really love it when it takes 1 hour only and not 3. And if you know P and Q, you can even decrease the work factor, which you would do if you had, if you were overzealous and you put it too high in the first place, and you notice that with your server you run into problem and denial of service and so on. So, availability of some of these features depend on whether you are doing pre-hashing and post-hashing or both. If you do the pre-hashing, you cannot, escrow no longer works because you'll get a hash of the password, not the password itself. If you do the post-hashing, you no longer store the big integer, but only something small. Small is beautiful. It's smaller. But then you can no longer do the offline work factor increase. So there's a choice. But at least you have the choice. Anyway, regardless of whether you pre-hash and post-hash or both, you can always do delegation, which I described here. Delegation works, it's a kind of masking. It's like RSA masking. It has been used for blind signatures, and it's the same principle. So you first, at some point, you generate some parameters. You do it only once. You don't. You can reuse them at length for many months or years. Basically, you're choosing random quadratic residues, that is random squares, and you square them, each of them, for your work factor. And you just store these alpha I and beta I values, and you need about 300 pairs. They are not secret values. You don't need to protect them, and you can show them, and you do them once, but they are specific to the work factor you are using. So you are encouraged not to use distinct work factors in all your database of hash passwords. You can, but it works better if they are all with 1 or 2 possible work factor values. And you can do that with only knowing the modulus. You don't need the factors. They help because you can do that faster with the factors, but it's not really needed. Then when you want to delegate, you have a number of squarings to do, and you want to push most of the squarings to another systems. The source system will do 1 squaring, and then it will multiply that values with a product of some of the parameters that we chose, a random selection. So we've got 300 of them, and on average, you'll make a product with 150 of them. Then you send the resulting value to the other system, which does all the squarings. And when the results come back, you cancel this multiplication by a product with the beta factors corresponding to the alpha factors which you used in the first step. So if you write it down, you see that it works, it's sound, you get the right result. What's a bit more technical is how it is secure. The main reason, it's because it relies on something known as the multiplicative knapsack problem. When you take random values, modulo and integer, and you multiply them, some of them together, you get something which really looks random. And it appears to be infeasible to determine whether a given integer, modulo n, is the product of some of your base or not. So with that, the delegation system, which was called B in the previous slide, will not learn X, and X is the square, X is the padded password, so we really don't want to show it. It won't learn the Y value either, which is the result of the hash. So it learns nothing which can be used to run an offline dictionary attack. So you can delegate the work to just anybody. Of course, if you delegate it to an hostile system, it can refuse to respond or return random junk, so it has the power of disruption. But it won't learn more, and it won't learn enough to attack the password. So the cost of delegation is about half the cost of a RSA private key operation. So a given server can do that thousands of times per second. So it's, then again, not free, but not too expensive. And the network costs are reasonable because they're just one round trip, and the values which are exchanged are the size of the modulus. So we're talking about 256 bytes. That's not too big. So now we've got delegation, but we still want something else, which is parallel hashing. So we want parallel hashing for basically two reasons. One of them is that there are some contexts where you've got several cores on your computer. Typically, you're doing some hard disk encryption, like TrueCrypt or whatever is fashionable today. And when you are trying to hash the password, it's because you want to boot up the machine. And once you want to boot up the machine, it's not available for anything else. So it has 4 cores or something like that, and they're just sitting, waiting for the hash to happen. So you would like to be able to spread the hashing cost to all the cores running simultaneously. And what I described just previously is very sequential. The sequence of squarings cannot be parallelized. Another reason when you want to have parallel hashing is when you are delegating to systems which are slower than you, and which are not only slower than your server, but really slow. Here I'm thinking about web browsers and JavaScript, and I'll give figures about that. And so you want to be able to spread one hashing operation to multiple delegating systems, delegating targets, such as web browsers, so that when you get all the answers, you can push them back together into one hashing. So and there's a simple method which works with just any password hashing. And in fact, everything I present here works with all password hashing functions, not just MACWA. It's generic. But with MACWA and delegation, it's a power combination. It's where it is really useful. So the simple case for turning a password hashing function into a parallel password hashing function is to do it this way. You are, instead of invoking the function 1, you are invoking it n times, 4 times if you have 4 cores and so on, with distinct source values and with lower work factors. Then you hash all the results you got and you XOR them together. And that's your parallel hash. And if you are an attacker and you want to cut corners and you don't compute all the hash values but only 3 or 4, three values instead of the 4, then you get nothing. Because that's the property of the XORs, and if one of the operand is unknown, you don't know anything about the result. And this relies on this extra hash function, which can be SHA-256, but it's an important property that the values which you get are unbiased and uniform. Okay, so this works, but this does not work well in our delegating system because just forgot to say something. This works well when we have one work factor because CPU cost is easy. If you can split it and you know they all add up in the overall effort. If your hash function are also a memory cost, analysis become a bit more complex, and since it's complex, I did not do it. So right now I'm envisioning functions which have only a CPU cost. So now we want to see the general case. We need more because if we are talking to JavaScript clients in web browsers, they are slow, but they are also unreliable. You are talking to people who connected in the few previous minutes, but you don't know if they're all still there. They can go away at any time. So you will need to cope with some of the delegation system not responding. So for that, we want to send, and we can't try again. That is, we could say, okay, we send to a few systems, and if some do not respond after some timeout, we try again the values with other clients. But then your overall processing time will be longer, and this won't work with the average user. Average user is not patient. We have to do one round where you send the work to do to a number of clients, and if sufficiently many answer, you should be able to complete. So there's a solution for that, but it requires some extra mathematics. You first need to work in a finite field. So basically, you're hashing things with a h function and you get bytes. So we are working in the finite field, the Galois field with 256 elements, and you're working byte by byte. You can read the definition if you want, but it's not really important. And then we're using our first full frame, which is Lagrange polynomials. It's been used since 1979 with Shamir secret sharing. So the idea is that a polynomial is a function, and a polynomial of degree at most t minus 1 is exactly defined by t values. If you know what that polynomial, that function gives for t distinct inputs, then you can rebuild it. But if you don't know at least t outputs for that function, then you get nothing. And that's the crucial point. If you have t minus 1 values, you know anything about what that polynomial would give as values for other inputs. So let's do it. We've got, we want to get answers from at least m delegated work units. We want at least m clients to work for us, and we require that at least m systems have invested in it for the effort, the computational effort of all these queryings to rebuild the hash values. But we will send more. We will send t requests, and we want that to recover from what we will get, as long as at least m will answer. Oh, 10 minutes? Okay. So you've got a password, a salt, the total work factor, same values as previously. So you still hash with distinct solve values and reduce work factor, and you get the HA values. And from the HI, you do that t times. So that defines you a polynomial. You rebuild it. Okay. And then you store some outputs for that polynomial, but not the ones you computed with hash. You store a number of them. Basically, if t is 15 and m is 10, you are asking for 15 clients to answer and you want at least 10 to respond, then you store 6 other values. That's what you do at registration, and you keep these 6 values. And when you want to verify a password, you ask again all systems to rebuild your HI, and from what you got as answers and the value you stored, you can rebuild the polynomial with enough redundancy to check whether it works. That is, you stored one more. In my numerical example, you ask for 15 values for the polynomial, you got at least 10, and you stored 6. So you've got at least 16 values. The polynomial was defined from 15 of these 16, so you can rebuild it from 15 of these values and check that the 16th works well with it. So at that time, you are really invoking T clients, and if you got at least M of them, then you're all set. So this way, you can take any password hashing function with a CPU cost, and you can make it parallel on unreliable clients. And unreliable clients, in the context of Macwa, are delegation clients. That is, the server is doing the administrative part with the padding and hashing, delegating to the clients, and for those who responded, reassemble the polynomials and check that the value corresponds. So this can be done by byte. Computation in that Galois field are easy. It's just a matter of table. That's 50 lines of code.
Are those unreliable but not discontinued clients? If one of those clients gives back a wrong answer or a corrupted answer, that corrupts everything else, right?
Yes. Okay. If you have a bit more clients who responded, that is, you want 10, but you got 11. If that doesn't match, you can try the reconstruction 10 times to see if there's a black sheep. And not only, and then if it finally works by removing one, you've saved the situation, and you know a client who doesn't respond well. Okay, so it's time to talk about performance. Okay, I'm lazy, so I don't do all the benchmark myself, but it so happens that all these queryings are very similar to what we do with RSA. So that means that we can implement Macwa efficiently, but using the same big number arithmetic libraries that have been optimized by generations of programmers for RSA. And we can use RSA as an estimator for the performance which we can achieve. So I'm building on that. So if you want to do the squarings, you use an existing library like OpenSSL or GMP or whatever exists in your programming platform. Montgomery's multiplication looks like the right way to do it. It's for the size of integers we're using, it's close to the optimal, as we know of. If you want to do the fast pass, there's a threshold at which point the fast pass is better than doing all the squarings. And if you are using Java, you want to use the modpo function from big integer, and it's a good idea. And it illustrates an interesting point. If you use an old Android system, the Java is really slow on it. But the modpo is really fast because it really is OpenSSL. It's native code. So you are getting all the speed you want, even on a platform which is not fast. And still worth the effort right now. If you are not fortunate that you're using JavaScript, then you don't have a nice native big integer, and you don't have actually nice integers. You've got floating point values, and you can get only 53 bits exact bits out of these values. So if you want to do the implementation, you're doing it with 26 bits per word, and so on. And you want to do the mathematical floor function, but you can get a faster implementation with the double tilde. It's a JavaScriptism. It looks like this. Okay, it's not very readable, but it's short. And really, here and here, there are about 20 other lines of code, but it's not hard to implement. And here is the performance. With the C code, with OpenSSL, on my computer, I've done an extensive benchmark on one computer, you've got more than 500,000 squarings per second. If you're using Java code, depending on you're using 32-bit or 64-bit implementation, you get various performance. That's the plain Java, which is originally from Suns and Oracle. So it's a big integer implementation, which is written in Java. And Java does not have a 128-bit integer types, only a 64-bit. So there's you lose performance, which is why it is 6 times slower than the C code. Whereas usually for computational tasks, Java is about 2 to 3 times slower than C code. But for big integers, you are 6 times, and it's expected. In JavaScript, you're about 20 times slower. It depends on the browser. Chrome is better than Firefox, which is better than Safari, but they are still in the same branch. And that's not a PC, so it's a Mac, so there's no Internet Explorer. And I've tried to implement in C, but using the floating points, just like the JavaScript code, and it's not even twice faster than JavaScript. So this means that JavaScript interpreters are actually quite good. They're doing a reasonable job. So this also means that they won't be really faster unless they begin to implement a native big integer library, which would be a good idea, and which might happen. So there's software, and then there's dedicated hardware. So for GPU, I did not do hardware an implementation, but I found a study from 2011, and it was comparing performance of CPU and GPU for RSA. So I'm assuming that performance for RSA can translate into performance for Macwa. And to my surprise, it so happens that the GPU was not really faster than the CPU. That is, if you count it per dollar with the hardware cost, or per watt, which is the cost of running the hardware, because that's the electricity and the cooling you'll need. So by all rights, the GPU should be much faster to run some macro code. But economically speaking, it's not worth it. At least it was not worth it 3 years ago. I don't have more recent figures. So I've looked also at what we could do with ASIC or FPGA. ASIC for doing RSA exists, and they're for hardware security modules, but they're very expensive and they're slow. And for both are for the same reason, because their value is not from their speed, but from their very expensive certifications, which ensures tamper resistance and so on. And it takes a lot of time and a lot of money to do a certification, so you don't want to do it again. So when you have an old design, an ASIC design, you keep it. So if you take a brand new hardware security module, the ASIC is a 10-year-old design in it. That's what is on the market right now. So it's not competitive with CPU. With some FPGA, some have a lot of DSP modules which know how to do some multiplication with rather small value, and you could theoretically use that to implement Macwa or RSA for that matter. But these FPGA are still very expensive when we're talking something like $5,000 or so on per FPGA. So when you factor the numbers, it turns out that it's still more expensive than a CPU-based solution. It's not technically it should be less expensive, but it's a matter of price, and price is not only technology, it's also economics. And from the economics right now, it seems that Macwa fulfills its promise. That is, the attacker will not get a power boost from using dedicated hardware. It was a surprise. I expected dedicated hardware to be 10 times faster for the same price, but I was wrong, and I like to be wrong in such case. So let's go to the conclusion. Delegation is something which may change. It's some people have said that it could be a game changer. I've not said it, but I think it. And but if you don't use delegation, then Macwa is still decent. It can defend its rank as a password hashing function. And implementation can use existing work on big integer and RSA libraries, and I think that's an important practical point. And right now it seems that GPU and FPGA are not up to it to break it. Okay, so I need more formal security proofs because I've waved my hands a lot that it's about an abstract problem, but I've not written a really decent formal proof. So if someone wants to do that, you're welcome. If someone wants to do some FPGA on ASIC implementations, they're welcome too, and it won't be lost because it could be turned into faster RSA implementation, which are useful too. So by all means, do it. I would like to have more statistics on JavaScript implementation in the field, so you have to try on multiple hardware and so on, and to try a full-scale experiment with delegation to tune the parameters to know how many parallel hashing you must do and what work factors. And for all that, well, volunteers are welcome. Any question? Yes.
Your claim about the speed of potential ASIC implementations seem to be quite in contrast with the situations for symmetric crypto or symmetric hash functions, where existing ASICs are like not 10 times as cheaper per watt, but say several thousand times cheaper.
Yes. Morally, ASICs should make short work of Macwa. But Macwa is all multiplications, and it turns out that for right now the CPU which are produced by millions are really good at doing multiplications. And in fact, a multiplication engine is a substantial part of a chip in a modern CPU, and we are building on that. Okay. I expect if Macwa is, let's hope, chosen as the winner, we might expect some people to come up with dedicated ASIC, which will be much faster than CPU for that task. And the strength of Macwa would then completely depend on the delegation capability. And that would not be even a bad situation, because at that time we would have very fast chips for doing RSA, which is also a good idea. But right now, although theoretically ASICs could compute Macwa very fast, right now they don't. So please implement them. Yes?
Going back to the comment, if someone knew keyword Q, does that make it vulnerable to plain text attack, or even logical portion of it?
If you know P and Q, if you know P or Q, you know both. Because from P you can just do a division and you have Q, and if you know P of Q, you are God. You have won. That's finished. You can take the hash value and recover the password itself.
And then, is there a specific reason why you derive the panic from the solve?
Well, the salt has to come into the, let's see, it's here. Here. Okay, this must be deterministic, and the salt must enter at some point, and I wanted to keep the password in clear in the padded value so that squo could work.
So it was to make it deterministic.
But it has to be deterministic because when you hash again, you want to get the same value. But it has to be deterministic but pseudo-random, because it must have something which looks like a random oracle here, because otherwise, if you keep algebraic values, you could get some cut some corners. You could share costs between multiple Macwa implementation, because it's a technical term, it's malleable. if you compute the product of two values and then raise these to some squarings, you get with 1 sequence of squarings the product of the two squared, multi-squared values. So with this padding and at least 30 bytes, you prevent cost sharing from happening. Yes?
If I was to deploy a system today, and I didn't know how long the system would be in operation, what guidance would you give me on choosing the length of that?
2048.
Even if it was 20 years?
It's fixed for up to 2030 in years. Right now, that's what NIST says. In my opinion, it will be fine much longer. But that's just my opinion. I'm usually talking of foreseeable future, and with technology, foreseeable future is no more than 20 years from now. After 20 years, it's no more foreseeable future. It's astrology.
We have to break it off. We're already into the break, and we have like 4 minutes until the next speaker in this room. So, a lot